Yeah, so this is a question from GATE 2016. The question is, consider the constant current source shown in the figure below. Let beta represents the current gain of the transistor. So this transistor has a current gain of beta. Okay, the load I0, the load current I0 through resistor RL is. So we need to find what is the load current I0 through RL. Okay, so if you analyze this circuit, this voltage is VCC and a Zener diode is connected here, right? So this is plus and this is minus, and this Zener diode is connected in reverse bias. So the voltage across this Zener is Vref. Okay, so if this voltage is Vref, what is the voltage across R1? So we know the entire voltage between these two is VCC. Between these two nodes is VCC. And Vref is dropped across the Zener. So the drop across R1 is actually VCC minus Vref. Okay, and in the circuit, this is connected to the non-inverting terminal. VCC minus Vref is connected to non-inverting terminal. So what will be the inverting terminal voltage? It will be equal to whatever is the voltage at its non-inverting terminal. So here also the voltage, will be same as V plus, that is VCC minus Vref. Okay, and that voltage is connected to this node. Okay, so if I draw here, this node voltage between these two node voltage is actually VCC minus Vref, right? So if this voltage is VCC minus Vref, again if you see, this node is actually VCC. So what is the voltage across resistor R? This is VCC minus Vref, right? So here the voltage will be equal to Vref itself. Okay, so there is a voltage drop of Vref across the resistance R. So what is the current I will call it as IR across the resistance. IR will be equal to Vref, that is voltage across the resistor R by the resistance R. Okay, so this is the current through resistance. And if you carefully see, we know the current going into the terminal of op amp is actually 0 ampere. So same IR will flow into this PNP transistor, that is, this will be IR. And what is this current? This current is actually the emitter current of the PNP transistor, IE. Okay, and we know here this current is actually IC, that is the current flowing through RL, which is I0, is actually equal to IC. I0 is equal to IC, and we know how IE and IC is related. IC by IE is actually equal to alpha, which means IC is equal to alpha IE, right? So I0, which is equal to IC, that is equal to alpha IE. Okay, and we know IR is equal to IE, so I will just substitute that alpha into Vref by R, which is IE, is equal to I0. Okay, also given the value given is not alpha, it is beta. So how alpha and beta is related? Alpha and beta is related as alpha is equal to beta by beta plus 1. So I will substitute this into this equation. So what I will get? I0 will be equal to beta by beta plus 1 and that into Vref by R, right? So that is I0. So the answer is B.
Yeah, so this is a question from GATE 2016. The question is, a PIN photodiode of responsivity 0.8 ampere per watt is connected to the inverting input of an ideal op amp as shown in figure. VCC equal to 15 volt minus VCC equal to minus 15 volt. Load resistance RL is 10 kilo ohm. If 10 microwatt of power is incident on the photodiode, then the value of photo current in microamps through the load is. So here the load is this one, RL, 10 kilo ohm. And question is to find what is the load current, say IL. Okay, so here we have the photodiode here, and a 10 microwatt power, light power is incident on the photodiode. So if this is the incident power, what is the current through the photodiode? So I'll call this IP, that is current through photodiode. IP is equal to 10 microwatt power is incident, that into its responsivity. Responsivity given is 0.8 ampere watt per watt. So 0.8 into 10 micro, which means that is 8 microamps. That is a photo current flowing through the photodiode. Now if we carefully see, the current into the inverting terminal is 0 ampere. So this current will be flowing through this load, right, or the resistance kept in the feedback. Okay, and if this is flowing like this, the voltage drop will be like plus here, minus here. Okay, and that corresponds to the voltage V0. So from the figure, V0 is equal to voltage drop across 1 mega ohm, that is feedback resistance. So 1 mega into 8 micro, which is the current flowing through it. So this is equal to 8 volt. So V0 is equal to 8 volt, and this is the same voltage across this load resistance RL, right? So what is the current IL? So the current IL is equal to the voltage across RL, that is 8 volt, by the resistance RL, that is 10k. So this is equal to 0.8 milliamps, and the question is in microampere, right? So this is equal to 800 microamps. So answer is 800. Yeah, so this is question from GATE 2016. The question is, an ideal op amp has voltage sources V1, V3, V5, etc. Vn minus 1 connected to non-inverting input, and V2, V4, V6, etc. Vn connected to the inverting input as shown in figure. So half of the input sources are connected to the non-inverting terminal, that is V1, V3, etc. Vn minus 1, and V2, other half V2, V4, V6, etc. Vn is connected to the inverting terminal of the op amp, right? And also given the plus VCC and minus VCC is 15 volt and minus 15 volt respectively. The voltages V1, V2, etc. Vn are 1, minus 1 by 2, 1 by 3, minus 1 by 4, 1 by 5, etc. So if you see here, the even terms are like minus, right? Minus 1 by 2, minus 1 by 4, minus 1 by 6, etc. As n approaches infinity, the voltage, the output voltage is, so we need to find what is the output voltage V0 when n approaches infinity. Okay, to solve this, we will consider the inverting and non-inverting nodes, and we will call this the voltage at this node as VA and VB. So, and we will call this as node as A and node B. Okay, and we will apply KCL at each node. So KCL at node B. Okay, so the net current at this node is 0, that is current flowing through this resistance, current flowing through this resistor, etc. Current flowing through this resistor plus this is equal to 0, right? So what is this current? That is VB minus V1 by the resistance 1k, plus the next current, that is VB minus V3 by 1k, plus etc. VB minus Vn minus 1 by 1k plus VB by 1k is equal to 0. So VB by 1k is this current. Okay, so if you see, denominator is 1k, so and all denominators same. I can take this two RHS, so I can remove this 1k resistance, right? So remaining is the VB terms and the sources. So there are n by 2, half of the voltage sources are here. So if you calculate this, the number of VB terms is n by 2 VB, okay, and remaining is the sources V1 plus V3 plus etc. plus Vn minus 1. Okay, or VB is equal to V1 plus V3 plus etc. plus Vn minus 1 by n by 2, that is VB. Okay, now similarly I will apply KCL at node A. Okay, that is at inverting node. So here again the current, if you see, the net current is 0, this current plus etc. This current is plus this current, right? Current through the feedback is equal to 0. So applying that, we can write VA minus V2 by 10k, so that is the resistance, plus VA minus V4 by 10k plus etc. plus VA minus Vn by 10k. So this is the current from the source plus the current through the feedback, that is VA minus V out, that is the voltage at this node, okay, by 10k is equal to 0. So again, as previous, 10k is common denominator, so I can take it to RHS and I can remove it. Okay, remaining is VA and the sources and output. So if you see, there will be n by 2 number of VAs available, minus V2 plus V4 plus etc. Vn, minus the remaining is V0 is equal to 0. Okay, or I can write V0 as V0 equal to n by 2 VA minus V2 plus V4 plus etc. plus Vn. Okay, now we know since it's a negative feedback, what happens, this voltage VA will be equal to VB, right? So VA is equal to VB, which is equal to from equation 1 V1 plus V3 plus etc. plus Vn minus 1 by n by 2, okay, from 1. So I can substitute this in V0. So what happens to V0? V0 will be equal to n by 2 into VA, I can substitute as VB itself, right? So V1 plus V3 plus etc. plus Vn minus 1, that is the voltage sources connected at inverting non-inverting terminal by n by 2 minus the remaining voltage, that is V2 plus V4 plus etc. Vn, right? So n by 2 cancelled, I have the voltage V1 plus V3 plus etc. Vn minus 1 minus V2 plus V4 plus etc. Vn. Now given values are V1 is 1, V2 is minus 1 by 2, V3 is 1 by 3 etc. Or I can say, right, Vi is equal to minus 1 power I plus 1 into 1 by I, right. If it is odd, right, if I is odd, this will be positive number, and if I is even, it will be minus number, like that, right. So if I substitute here, it will be like V1 is 1 plus V3 is 1 by 3 plus 1 by 5 plus etc. plus 1 by n minus 1, okay, and this is minus 1 by 2 plus minus 1 by 4 plus etc. minus 1 by n, okay. So if I take minus inside and club both the terms together, I will get, okay, it will be a summation of these terms, or I can write as 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus etc. plus 1 by n, or I can write as sum of say n equal to 1 to n 1 by n, that is V0, okay, and we know the value of this term is equal to infinity, sorry, not 0, infinity, okay. This value sums to infinity, but that's, which means V0 actually tends to infinity, but we know it's an op-amp circuit and it's an ideal op-amp, so its V0 won't go to infinity, right. It will be like saturated, it will be saturated to 15 or minus 15 value, that is the maximum value it can reach, which means what is the value of V0? V0 will be equal to plus 15, which is the maximum value, that is infinity means it saturates, okay. So answer is V0 will be equal to plus 15 volt. So this is a question from GATE 2016. The question is, the following signal Vi of peak voltage 8 volt is applied to the non-inverting terminal of an ideal op-amp. The transistor has Vb equal to 0.7 volt, beta equal to 100, VLED equal to 1.5 volt, VCC equal to 10 volt, and minus VCC equal to minus 10 volt. Okay. The number of times the LED glows is, so we need to find if this is the Vi signal, okay, applied here, how many times this LED will glow. So if you carefully see, the on voltage for this transistor, that is 0.7 volt, and the input is connected through this op-amp circuit, and if you see here, this acts as a comparator, right, there is no feedback. So whenever the Vi voltage is greater than this node voltage, that is voltage at this inverting terminal, then the voltage here will be plus 15, plus 10, because its bias is 10, or else it will be minus 10. Whenever it is plus 10, that is when the op-amp is like output of op-amp is plus 10, what happens, definitely this transistor will be on, and if the transistor is on, there will be flow of current like this, and when this flows, the LED will glow, right. So that's what happens. So what we need to do is, like, we need to find at what voltage Vi does this op-amp output is plus 10, okay. So here for that we need to find what is V minus, okay, V minus. So if you carefully see here, V minus is the voltage across the 2 kilo ohm resistor, and this is a potential divider. So what is this V minus? V minus is V minus is equal to the total voltage 10 into the potential divider, that is 20k 2k by 8k plus 2k. So if I write here, V minus equal to 10 into 2k by 8k plus 2k, or 20 by 10, that is 2 volt. Okay, so here the voltage is actually 2 volt. So whenever this Vi is greater than 2 volt, definitely the output will be on. So if you see here, this is the 2 volt, right. So the output of op-amp will be high whenever this signal is greater than 10 volts. So if you see, this is the area for which the input signal is high, okay, or greater than 2 volt, which means the output of op-amp will be high in that area. So if I draw here, okay, so if I draw here, I can draw like this. The output of op-amp, so I will call it as VOA. VOA will be high during this time period. Okay, for the other remaining time period, it will be like minus 10 volt. So this is plus 10 volt and this is minus 10 volt. So the diode LED will be on whenever VO is 10 volt, plus 10 volt, right? So during this time period the LED is on. So how many, question is the number of times the LED glows when this signal is applied. So what is the number of time when LED glows? It is 1, 2, 3. So it glows 3 times in the for this given input signal.